Let us present S3K, Self-Supervised Semantic Keypoints for Robotic Manipulation via Multi-View Consistency. Within this paper, we show how to use keypoints to solve tasks such as grasping a deformable object or inserting a flexible cable. The goal of S3K is to detect keypoints in images. We do it by using a small number of human annotations which semantically define the keypoints. The novel part is using a large corpus of unlabeled data to gain robustness. This can be seen as reducing the hypothesis space of potential detections to geometrically meaningful interpretations of the few labeled samples. The network architecture is inspired by the UNet. In our case, the input is a single image and the output is a set of heat maps, one for each keypoint. During the supervised training, we have the keypoint location for each frame. Therefore, we can project it into the individual camera planes. Predicting these image locations creates a supervised loss. However, we can't do this during the self-supervised training as we do not have the 3D locations. Therefore, we have to bootstrap from our own predictions. To do this, we first acquire a prediction from each camera. But this might be uncertain. Here we represent this with a thinner arrow. Then, we infer a 3D location which should be at the intersection of the most confident predictions. This 3D detection is then used as a label, just like in the previous case, and projected back into the individual cameras to obtain the self-supervised loss. In our experiments, the first question we wanted to answer is how well the model can use this unlabeled dataset. We created a simple simulated environment with a single object and 4 cameras, and randomized their poses. We explore the impact of increasing the amount of labeled and unlabeled data. Our metric is the pixel error on novel poses. To analyze this, we plot the error as a function of total data, labeled and unlabeled, and denote the ratio between them by the point color. If labeled and unlabeled data were equally valuable, we would expect all of the points to lie on a line independent of color. The points on the top represent cases where only 3 labeled frames are used. This is not enough to ground the model. But we can see that the rest of the points follow a common trend independent of color. This means that the ratio is not important anymore and the performance is correlated with the total and not just the labeled data. Therefore, robustness can be achieved by using more unlabeled data. This is the core result which enables the S3K approach. Next, we explore the ability of this model to generalize across objects of the same class. To do this, we annotated key points on 16 shoes. We used 12 of them for training and the remaining 4 for testing. This video shows the detections from 4 cameras on the 4 unseen shoes. The model is successfully able to detect the tip, heel, and tongue of these shoes. In our experiments, we wanted to see whether we can use this model to script a controller that can grasp a specific part of a deformable object. In our case, the front right paw of a plush fox. To collect the data, we used a scripted controller which hovered above our object. We gathered 21,000 images from 7 different arrangements of our objects. For each arrangement, we annotated 5 key points on the plush fox. Finally, we scripted a policy to perform a grasp based on the front paw. The training dataset only included data collected while hovering, and therefore the model does not perform well when close to the table or when the fox is grasped. However, it is accurate enough to repeatedly perform a grasp of this highly deformable object. In some applications, however, we might not be able to script a controller directly, and we might need to train an agent using reinforcement learning. To explore this, we use a flexible cable insertion task. Our approach is inspired by the Adriat agent, which is based on learning from demonstrations. We collected 51 human demonstrations which were used by the agent and the vision model, and included some extra data for the keypoint detector only. The final dataset had about 3000 timesteps. In 121 of these, we annotated the plug tip, base, and socket locations to semantically ground the key points. To evaluate the vision model, we teleoperated the robot to various interesting states. We can see that it is capable of robust detection and therefore can be used as a real-time tracker. The model is capable of detecting the plug tip even when it is difficult to discern it from the background. The output from the model provides sufficient information to the RL agent for it to successfully solve the cable insertion task. Using key points as visual features significantly outperformed using VAE latent features. Our agent trained faster and reached a significantly better final performance. Further information available in our paper and on our project website.